and we didn't quite get all the way through here. We were doing these things called line integrals. And we had got to the point where we could find the area of a curtain that we dropped down off a surface. And we talked a little bit about the paths and how if you reverse the path, that might have an effect on the value of the line integral. If the path doesn't matter, then we call it path independent. And then I said today what we would do is we would extend this concept, but now our curve C, instead of it living in two-dimensional space, we're going to let that curve live in three-dimensional space. And we can still define a line integral, all right, the same way that we did in 2D, in 3D, but we just can't visualize it. So let's say we have a curve C that is defined with a set of parametric equations. So we're going to have one additional piece to this, and that's we're going to have a Z equation. Now, I'm going to use some different notation this time. So there is a slight tweak to our notation today. Instead of writing this, this curve in its parametric form, I'm going to write it in its vector form, because we know that we can draw curves in three-dimensional space with vector functions. So we'll write the vector r of t, this function, is equal to the vector x of t, y of t, z of t. So the x of t, y of t, z of t are the component functions of our curve. Then the line integral of the function f, what type of function is this f? We said scalar, right? We call it a scalar function. So the line integral of the scalar function f along C is given by this equation. Now that's the notation for it. All right, so that notation is exactly what we did last time. The only difference is the z in here. ds still represents the what? Arc length. Okay, that ds is the representation of the arc length. And so when we convert this over and you say f of x, y, z, you're going to replace your x with the function of t that you have for x, which comes from the curve C. You replace the y with the function you have for the y component and the z component. And then this is your arc length formula. But in three-dimensional space, your arc length formula changes. Okay, right? This is what it changes to. So you just have that additional dz dt squared. Now this right here is where the notation really changes. All right? So what I want you to notice is that this right here, by its very definition, is the magnitude of the derivative of the vector function, r. So remember, if we have a vector function, r of t, which was given to us, right, by x of t, y of t, z of t, then if I ask you for the magnitude of the derivative, right, the derivative of this, you would just take derivative of each one, which I could say dx dt, dy dt, dz dt, and then you take the square root of each of those squared, and that's what this is. So what we recognize is that that piece is this. It's just a different way of writing this line integral. And another way of writing this is going to be to use this notation. I wrote it in red here. I don't think that's in the notes that I put online. Okay, I don't think I put that in the notes. And that's, what do we mean by f of r of t? So what do we mean by this? Because we've never seen this. We're taking a function and plugging it into a scalar function, right? Taking a vector function, plugging it into a scalar function. So this is a notation thing. What this actually represents is you're going to take the x component, right, and plug it into the x on the scalar function, the y component of the vector function r of t, plug it in for the y, and then the z component function, plug it in for the z. It's just weird. It's weird to plug a vector function into a function, so we have to understand what it means when you write this down. Okay? Let me give you an example. Look, if I give you a function of 3 variables, and I tell you it's x times y times z squared, I think everybody is comfortable with me saying plug in 1, 2, 3, right? If I say plug in 1, 2, 3, everyone would say, oh, okay, that's 1 times 2 times 3 squared, right? That's what that would be. And so your answer would be what, 18? But what if I said plug in the vector 1, 2, 3? Do you see how that's kind of strange to say that? Because normally we just want to plug in like a number, 1 and then 2 and then 3. But I'm asking you to plug in a vector. And that's what I'm doing here, right? So what we mean by this notation is exactly to plug in whatever this component is, plug it in 1. Whatever this component is, plug that in for the y. Whatever this component is, plug that in for the z. So they are the same thing. Okay, it's just a notation thing. Okay, that's all it is. All right. All right, now if you recall from last class, when we did a line integral, initially we did it with respect to arc length. And then after that, we did it with respect to x, and then we did it with respect to y. Well, now we're going to have a similar thing, line integral of the function, the scalar function f along c with respect to x means instead of having that big old square root thing out there, you just have x prime. With respect to y, same exact thing, except just y prime. And then with respect to z, just the z prime. So we have 3 new versions of line integrals.
Why do you have to split it like that?
Here. Okay? So again, the previous 3 line integrals are used in later sections, okay? We will use them. In the event that we use, in that event, we will use the following notation. So what we have is, we're going to have this later. We're going to have a line integral of the scalar function p along c with respect to x, plus another line integral of the scalar function q along the curve c with respect to y, and then the r function along c with respect to z. And that's the notation. Instead of writing 3 integrals, since they're all going along c, we just write 1 integral and all of them together. So right now we don't know why this is going to have value to us, but it will be useful later for us to do integrals with respect to x, y, and z separately instead of with respect to arc length. All right. Okay. Those of you who turn this in after class start are not going to be happy with me, but I'm not very happy either. So these are due at the beginning of class. It's kind of become a little bit of a habit that people are coming in late, disrupting my class. I don't find that to be very respectful. So everyone who turned it in on time is getting a 10-point bonus. Everyone who turned it in late, which is everyone in this stack, is getting a penalty. I know you're not going to be happy about that, but that's life. You turned it in late. Should we continue? Sorry, I hate doing shit like that, but I don't think it's right to disrupt class like that and turn stuff in late. It's not right. Okay, find this line integral where c consists of the line segments from 0, 0, 0 to 1, 2, negative 1, and from 1, 2, negative 1 to 3, 2, 0. Everything is exactly the same as last class, with the exception that we're in 3-dimensional space. Our curve is. So we still have to come up with parametric representations or a vector function which represents these segments. So how about we look at these segments, we break them up into 2 pieces. We call this one C1. Why don't we call this one C2? That seem fair to you? right? For C1, I imagine that I'm going to be going from the point 0, 0, 0 to the point 1, 2, -1. I'm not trying to draw this in three-dimensional space, all right? Because I'm kind of conceding that I'm not going to be able to do it real good. So I just know that I need my C1 to connect those two. And I want to go in this direction, from there to there. So how can I come up with some way of representing that either in a parametric form or as a vector equation? You could do, okay, so what vector equation are you going to use? Like how are you?
Find the direction vector.
Okay, so this is a line segment, right? So we've done this before. It's just now you're in 3D. So we're still going to use the fact that R of t, we could do this one, right? R naught plus TV. We can do that. That should give me, I should be able to draw that line if I can put everything in the right way. So what's R naught going to be for me here? 0, 0, 0, that's where I'm starting. So R of t equals 0, 0, 0. And t, and then how about the direction vector? It's the vector that goes from here to here, so you subtract 1 minus 0, 2 minus 0, -1 minus 0. So it's just that vector, isn't it? That point written as a vector. 1, 2, -1. And this just turns out to be, I'll do it right here, R of t is t, 2t, -t. Okay? So we're breaking up our C into two pieces, which means I can integrate along C1 first, then come through and integrate along C2. So I'll let you choose where we go from here. Would you like to go get C2 now, or you want to just do this integral over C1 first and then come back and do the C2 one later?
Get C2 now.
You want C2 now? Yes? Okay. So we have disagreement. I don't know what you said. Okay, I'll get C2 now. Okay, what about C2? Yeah, I'm gonna connect from 1 to -1 over to the point 3, 2, 0. I'll call this R of t again. I guess I could use a different notation, right? If I wanted to not confuse the two. I could maybe do like R sub 2 and R sub 1, right? That might be a way of distinguishing these two from each other. Not necessary, but probably good math penmanship, I guess you could say, to kind of distinguish these. R naught, 1, 2, -1, that point, written as a vector, plus t times the direction vector, which is the vector connecting from here to here, so 2, 0, 1. And then when you put this all together, you get 1 plus 2t, 2, -1 plus t. So you can write -1 plus t, you could write t minus 1, whatever. Any questions on the parameterization of that? So I'm keeping these as vector functions, right? I'm not writing them as parametric equations, but I could easily do that, right?
Yeah.
Okay. All right, I think I'm ready to set this thing up. And I'm erasing everything I'm going to need. All right, the line integral of x squared dx plus y squared dy plus z squared dz along the curve C is equal to the same thing along C1 plus the same thing along C2. DZ, thank you. Questions? So I'm splitting up C into its two pieces. Now I need to actually figure out what each of these pieces are. Is this allowed? Tell me if this is fair. Yes, that's what the property I just showed you before said. I can't put it up here, it'll just be jumbled up. If you look back in the notes, I think one note before this, that's property. This means this. Okay, let's try this first one right here. So I'm looking over C1. I'm going to replace this x squared with whatever my x component function is. What was the x component function on C1? Actually, you can tell me right here so I can write it down. It was t, then what? 2t minus t. Okay, that was r1 of t. r2 of t I've got down here, right? So I'll use that in a second. This is r2 of t. All right, so because I'm on C1, I'm looking at this. The x component squared, so this is going to be integral t squared. And then what's dx? What's the derivative of the x component? Just 1, right? Derivative of t is just 1. So it'll be, well, you should say 1 dt, right? 1 dt. So dt. Any questions on where that came from? Plus, what's my restriction on t? Ooh, I forgot to talk about that. Oops. Both of these are 0 to 1. Why is it 0 to 1? Because that's the way it worked, right? If you set it up the way that we've done, that I've told you since the very beginning, then t will always go from 0 to 1. Now that's important because I need to put limits of integration on this. So 0 to 1. What's my next one? Still looking over C1, so I'm still looking at that function. What's the y squared?
4t squared.
So it's 4t squared. So I'm squaring 2t. So integral 0 to 1, 4t squared. But then dy, what's the derivative of the y component function? 2 dt, right? So I'll put here 2 dt. Plus integral 0 to 1 again. Last one. Z squared. Negative t times negative t is t squared. And then what's dz? What's the derivative of z? Negative 1 dt. Follow? Plus, we keep going. Now we're looking over C2. So I'm looking at this one. X squared. 1 plus 2t squared. dx. What's derivative of this with respect to x? Derivative of this with respect to t. I don't know why I said x. 2 dt. Plus this integral. 0 to 1 again. Y squared, which is just this. What's going to happen? 4 times. What's the derivative of that? 0, because it's a constant. 0 dt. So that integral is not going to contribute at all. And then dz dt. I'm sorry, z squared dz is going to be, I'm going to have to push this right in here. Integral 0 to 1, negative 1 plus t squared. And then the derivative of this is just 1 dt. So there you go, dt. Any questions on where any of that came from? All of these integrals happen to be from 0 to 1, don't they? All of these integrals happen to be with respect to t. So I can turn this into one big integral, can't I? Sometimes that won't work. Because if C1, let's say, went from 0 to 1 because it was a line segment, but C2 happened to be part of a circle, that might go from like 0 to pi or something, then you can't throw them all together at the end. But in this case, I can. And I should just have big old polynomial, right? Let's see if I can't get this written down. This will be equal to just one big integral, 0 to 1. Try and clean this up. I've got t squared here. And here we've got, what, plus 8t squared. And then this one, minus t squared. And then this one, let's do some algebra here real quick. This is 1 plus 4t plus 4t squared, right? That's what this is. Then times 2. So how about plus 2 plus 8t plus 8t squared? Understand what I'm doing? Okay, and then here, nothing, and then square this one. 1 plus, or 1, what is it? 1 minus 2t plus t squared dt. I think that's all of it, right? Now collect like terms, and I mean, we were already there, but I decided I would take this the full way. How many t squareds do we have? 3? 5? I'm not even looking, y'all tell me. 5? Okay. We're all agreeing with 5? Okay. No? No? Do I need to count? 17? Okay, 17? You changing your mind? All right, 17 t squared? Okay. How many t's? 6 t's? And constant. We do have constant 3 dt. And I've come this far. Antiderivative 17/3 t cubed plus 3t squared plus 3t. Evaluated those 2 points. When I plug in 0, it goes away, so I'm happy about that. When I plug in 1, I get 17/3 plus 3, which is 17/3 plus 9/3 plus 9/3. So 35 thirds. What does this number represent? It's the line integral of along this curve C of this, right? That's what it is. I can't assign the same meaning to it that I did last class where it was like area of curtain. I can't do that. It doesn't make, kind of like when we're trying to find, doing triple integrals, and we couldn't really talk about it as being like a volume anymore. It was like something else. All right, let's see what's up next. All right, remember back from earlier chapter, we talked about work. And this is something you probably did in physics too, if you've taken it. Work is defined to be your force vector dotted with your displacement vector. So if you're dragging a cart across the ground like this, right? You're applying a force, and that force can be viewed as having an angle, right, and a magnitude. So you have a direction and magnitude, and then as you move the thing around, it's going to move from one place to the other. It's going to have a displacement vector also. Work is defined to be the dot product of those two. So generally speaking, I have the computer actually calculating the work right now. It's taking this vector and it's dotting it with this vector. So if I change my force vector and I make it longer, apply more force, I'm doing more work. All right, less force, I'm doing less work. If I change and I make it where they're parallel to each other, right? what happens? If I move this up, what happens to the work? It's going to get smaller. It's going to go to 0, actually, once I get perpendicular. And then if I go this way, I get negative work. All right? All right, so this is a review. You've seen, hopefully, that. All right, now let's imagine a point moving along a curve C within a vector field. All right, so we have some curve C. Right now, let's just look at two-dimensional space to make this easy. And you're moving along this curve from one point to the other, but this curve lives in a vector field. So remember, a vector field has nothing to do with this curve, right? You just have a vector field sitting here, which means that at every point, there's a vector, right? Every point, there's a vector. So at every point on this curve, there is a vector. There's a vector doing something. I don't know what it's doing because I don't even know what the vector field is. I'm just making it up. Okay, that's what's happening. But there's vectors everywhere. Just along that curve, there is your vector field vectors. An example of that would be an electromagnetic field or a gravitational field. You know. Then the total work done by the field is the sum of all the work done at each point. So what we're doing is we're trying to move something from here through the vector field to some other point along the curve C. As I move, I have displacement, right? Yes, I'm displacing the point. And at every single point, there is a vector that represents the field vector. And so you can look at this as being like the F that's pulling it. And then you can say the distance we travel in this direction is the displacement, right? Understand? If we dot those two together, right there, I'll get the work done right there. But see, there's a problem with that. How can you have work done at a single point? You have to have displacement, don't you? So what we do is we do it on the infinitesimal. We take an infinitesimal point. Well, that doesn't make any sense. We take an infinitesimal segment of the curve. So what can you tell me about this displacement vector? How do you think it's related to the curve itself? It is tangent, right? Do you agree that that black vector right there, which is pointing in the direction of my displacement, should always run tangent to the curve? So like when I get over here, my displacement vector should be running tangent like this. Then I have the force pulling me. So should I just take all these vectors, the blue vectors, the vector field, and just dot them with the tangent vector? Not quite, almost, because this tangent vector changes as I move. And does anyone remember how the length of this tangent vector relates to the curve itself? It's what? I think you were right, if I heard you right. Speed. It's the speed, exactly. So the longer the vector is, the faster the particle is moving, right? So we don't want the speed to have an effect on the displacement, because speed and displacement aren't exactly the same thing. So what we do is this. First, we try and create all these black vectors. Let's just make them all unit length. So they all have the same length. How do we do that? So let me remind you, isn't this right here the tangent vector? Yes? What is capital T? That's this vector, the tangent vector, divided by its own length, right? Which gives you a unit vector. So let me start by doing that. I've got all my force field vectors out here, right? Vector field vectors. And then I have all these tangent vectors that are changing length, and I'm going to do this first to go ahead and make them all unit length. So they all have the same length of 1. Then I'm going to scale that unit length down to make it an infinitesimal. How would I scale this unit vector down to make it infinitesimal here? What should I approximate that little infinitesimal with? what do you think I should use? How long is that little infinitesimal, that little tiny little, that little infinitesimal piece that goes from here? What could I use to approximate that little tiny, tiny little thing? The arc length, right? Isn't that how we approximated it last class? If we want to approximate how long this is, we just used a little arc length formula. So that's what I'm going to do. I'm going to take the tangent vector, I'm going to make it length 1, and then I'm going to scale that by the actual arc length, infinitesimal, and that will give, that'll pull that back so that it'll give me the displacement. I hope that makes sense. That's exactly what we do. All right, so let me show you the formula on the next page. The picture I have of this, you can kind of see what I'm talking about. Well, maybe not. Oh. So there's a curve. There is a, I want these to point in the same direction. I guess that's not going to happen. Good enough, right there. So I'm moving from this point over across like this. So when I'm at this point right here, my vector field's pulling me in that direction, right? And this is my unit tangent vector. I don't want to use that length because that's not my displacement, right? But I can say it's pointed in that direction, but it's this little infinitesimal arc length. So you get this. We can see the work done is that force vector dotted with the tangent vector, which is length 1, but then scaled by the ds, which is the arc length. And if I rewrite this, right, moving the scalar to the other side using properties of dot products, this is equivalent to this. The total work done will be the line integral, right? The sum of all these little pieces of f dotted with t ds. Now what sucks about that formula is that in order to use it, you have to compute capital T, right? And capital T requires some work, doesn't it? Because you have to take the derivative of the curve function, you have to scale it by its own length, and that requires work, right? Understand that that would not be fun? But let me write this down. What is capital T? We said it was the derivative of r, right, over its own length, right? And then we have times ds. Now be careful here. This is a dot product. This is scalar multiplication. Okay, that's scalar multiplication. I forgot my absolute value here. But what is ds? What's ds? That was what? That is the arc length, but I just gave you a note that told us what ds was. Do you remember it was this? It was the square root of dx dt squared plus blah, blah, blah. But I said if we look at the curve as being r, that really is just what? The magnitude of r. Whoa. So this is just the magnitude of r of, magnitude of r prime, not of r, right? Because these are all the little derivatives. So this is the magnitude of derivative dt. And do you see what happens? These cancel. And so you get the cleaned up version of the work formula for a particle moving along a curve in a vector field, which I'll put up on the next slide. We could have used capital T, but why compute it if we don't have to? All right, so this is me basically explaining what I just explained on the board with this, that they get cancellation. And so work turns from this after cancellation into this. So all we're going to have to do, if somebody gives us a curve, right, and somebody gives us a vector field, and they ask us for the total work done, we're going to need to take the dot product of the derivative of the curve, which hopefully we'll be able to find the curve and then take its derivative. And then we'll have to dot that with the, what does this mean? The vector field with R of t plugged in. That's a little strange looking.
Don't we just plug in the components into the...
That's right. We're just going to take each component function of our curve and plug it into the components of the vector field. Because remember, as you move along the curve, right, as I'm drawing this curve, when I say I'm at that point, that means that there is a vector, R of t, that takes me from the origin to that point, right? Then there's a field. And the field, F, you need to tell me what's happening at that point, right? What's the field vector look like? Well, where are you? I'm at R of t. That's where I'm sitting. So you're going to plug that vector into that function, and that should spit out the vector for the field that's at that point. You'll see, but it's one of those things that's the notation's kind of strange. This is the general formula. So there's one little thing that's different, which on the board right now, that I didn't have up before. So let me run through this. We call these line integrals over vector fields. What we were doing before were line integrals over scalar functions, right? We were doing line integrals where the f that we had in there was a scalar function. Now the function we have inside is a vector function, capital F. Suppose that f is a continuous vector field defined on a curve. And you have some way of parameterizing that curve. So you have generated the vector function that draws the curve. You also know what your restrictions on t need to be to draw the entire curve. Then the line integral of the vector function f along c is exactly what I just told you a second ago. All right? It's this dot the derivative of r with respect to t, limits are a and b. So that's exactly what I had before. This is where it came from, isn't it? That's the idea of scaling the tangent vector and all that crap. But this over here is the new notation for it. This is the notation. And what I want you to see from this is that, do you remember how ds before, d little s, represented the arc length? So it was the square root of all that junk. Now, when we see this, dr, and not dr scalar r, dr vector r, right? d vector r means this. It is the derivative of the vector curve, or the curve function with dt. Does that seem reasonable that this notation represents this? Okay. All these little ds, dr, they're subtle, but they're so important because later on we're going to have, I think I told y'all later, we're going to have like d capital S or like d capital S vector S, and they all mean something different. So we need to be clear on what's what, when it's a vector, what it means. When it's not a vector, what does it mean? So I'm just trying to point these things out. All right, here we go. One other thing, if you reverse the path, right, if I go integrate over negative c, it's the same as going over c but changing the sign. So when you're doing line integrals along vector fields, then path matters, right? The direction matters, but it just switches your sign. All right, finally, an example. find the work done by the gradient vector field of f of xy equals x plus y quantity squared on a path traversing the top half of the unit circle in a counterclockwise direction. Boy, I sure do like that top half of the unit circle, don't I? Find the work done. Well, here's what I know. Work is defined to be the line integral along C of my vector field dotted dr. That I have to know to start the problem, right? Which is the line integral along C of f dotted with r prime of t dt, right? That was the second. Well, actually, that was what we got after we converted the tangent thing over. This was just purely notation. So I need to know a few things. I need to know r of t, which is what draws the curve, right? And I need to know capital F vector, which is the field. Ideas? Any suggestions?
This is a unit circle. Can you draw it out?
Okay, so you want to start with trying to get r first?
Yeah.
Okay, let's try and find the vector function that draws the top half like this. And you want to go counterclockwise, right, like this? You want to start here, unit circle 1, you're going to end here at -1. Now we've done this, I think, twice now, right? At least twice. But we always wrote it as the parametric equations. So we wrote it as like x would be, in this case, cosine t, and y would be sine t, and then we'd say t varies between 0 and pi, right? That's what we did last class. We just need to convert this over to an r of t, a vector function. So we'll just write r of t equals the x is cosine t, the y is sine t. And that should draw the circle, right? The half semicircle there. Right, there it is. We all agree that draws it? Okay, so r is taken care of. What's the field? What's the vector field?
Gradient of
It's the gradient vector field of this. And if you did your homework, which I know all of you are doing your homework, I know that for a fact. I've been a little frustrated lately. I mean, I hate to say it. I'm kind of coming down on you all a little bit today. But I get a lot of these homework, or a lot of these questions about these take-home tests. And I'm like, have you done the homework? No. You're not, I mean, you have to, not every problem's like this, but the idea is that if you do your homework, the take-homes are a lot easier because you've at least been led into it. But I don't see that happening. Okay. I'm not here to babysit, okay? What's the gradient vector field of the scalar function, f?
It's going to be a vector with partial x, partial.
That's right, good. So you're looking at, when you say gradient vector field, everyone here needs to know what that means. That means the gradient of the scalar function f, which by definition in this case is the partial of f with respect to x, partial of f with respect to y. It's only two-dimensional because, well, f is two-dimensional. This gradient vector field, right, this right here, is the capital F they want us to use. So my capital F will be what? What's the partial of f with respect to x? 2 times x plus y. So you're doing like a chain rule on this. 2 has to come down, and then you do derivative of what's inside with respect to x, which is just 1. So you get that. Then partial with respect to y, same exact thing, right? There it is. You know what? I don't like my notation. I forgot something in this one right here. What did I guess I could have got away with it, but the way it was written in the previous note, what am I missing right there? F with what plugged into it? R of t. If you look in your notes, which again, I know all of you have printed out the notes and have them with you and keep them in class, and then this means I'm going to plug the vector curve into my field, right? And there's my field. Here's my curve. Here's my vector curve. So let's plug it in. I think I'm ready to set the integral up. What's my integral going to go from? What's my restriction on t? 0 to pi? All right, let's take my curve and plug it in to this. That means I'm going to replace every x with cosine t, every y with sine t. So this is going to become the vector 2 cosine t plus sine t. Then same thing, right? 2 cosine t plus sine t. That's the first vector. I'm dotting that with the derivative of my curve. Now, the derivative of the curve, I hadn't written that down, but I'll do it right here. What's the derivative of that curve function? How do you take the derivative of a vector function? Component by component, right? So what is the derivative of my, what was the x component of my r? Cosine t, so derivative of that, negative sine t. And then the y component was sine t, so derivative of that is cosine t. Y'all know what I'm doing there? That's going to be dotted here. That's what's going right here. So that is negative sine t, cosine t. And finally, dt. When you take the dot product to two vectors, you get a scalar, right? Or in this case, we're going to get a function, but it's going to be a scalar function. The point being that when you dot product two vectors, you don't get a vector. So I have this now. Integral 0 to pi. And dot products, those were pretty easy, weren't they? You just do first component times first component plus second component times second component. So let me do that. How about I do this? I'll make it negative 2 sine t. That's the 2 times the negative sine t. And then I'm going to distribute it through. So cosine t and then negative 2, what? Sine squared t. That's what you get when you multiply this one times this. And then when I do this one times this, I get plus or minus? Plus 2 cosine squared t. And then plus 2 cosine t sine t. Yeah? dt. Does anything good happen here? You can take a 2 out. Yep, you can. I see that. Do you see that? It's gone right there. Unfortunately, that's not a Pythagorean identity, right? Okay, so I can do this. Let me take a 2 out. Integral 0 to pi. And if I took a positive 2 out, these would flip places and be cosine squared t minus sine squared t dt. Which what?
Was the double angle cosine?
Is that double angle cosine? I'm just wondering how many of you are comfortable with that being double angle. Most students are familiar with this one. I hope. right? That's one that a lot of us kind of got memorized by now. But for cosine 2t, there's 3 of them that you could use. What's one of them? Cosine squared t minus sine squared t. What's another one? 1 minus 2 sine squared t.
And then 2 cosine squared.
That? So where are those? If you don't know those, where are they? They should be on your formula sheets, right? Not that one though. Yeah, not that one. The ones that you're allowed to have for the class. It's the pre-cal, one of the first pages on there. So if we believe this, then that right there is cosine 2t, which is 2 integral 0 to pi cosine 2t dt. Antiderivative of cosine is sine, but then we have to scale out because we got a 2 in there, so 1/2, right? But then the 1/2 and the 2 out there are going to go away. So this is just sine 2t, isn't it? It's the antiderivative. 0 pi. Sine of 2 pi is 0. Sine of 0 is, oh man. We did 0 work. Now, I know that's all for nothing, okay, but the value of the problem was not in the fact that we got an answer of 0. If you look at the geometry of the problem, okay, the vector field is drawn here for you. And we're moving along this unit circle in the counterclockwise direction. Just take note of, as we move this around, right now, is my work positive or negative? It's a dot product between these two vectors, right? Dot products are always positive if the angle between your two vectors is less than pi over 2 or less than 90 degrees. So you can tell from this that I've got less than 90 degrees. So I'm getting positive work here, right? This is all positive work. And then as I move around and I get over to about right there, now it's opened up, hasn't it? Now I'm getting negative work. And then over here, I've got positive work again. So what we have total, like a total work, right, would be 0. So what might make this problem a little more interesting is to maybe only go from this part to here, right? And all that would change is we would go from 0 to what? Pi over 2, and then we'd do all the work, everything else would be the same. So we'd be integrating 2 cosine 2t dt, and so we'd be doing sine 2t 0 to pi over 2. We already know that when we plug in 0, we get 0, but when we plug in pi over 2, what do we get? We get 0 again. Okay, so what does that mean? We plug in, we get 0 again? Does that look right? Did we have negative work back there? Let's see. This was positive work, right? Get over here. And right about past there, we get we start getting negative work, so they're canceling. So maybe we do pi over 4, right? and we're going to get some work in here. So we do pi over 4, right? And now that's what, pi over 2. Sine of pi over 2 is 1, so you'd get 1, right? The idea is that you're getting positive work and negative work together here. At the end, it turned out to be 0, but that doesn't mean no work was ever done. Yes?
Did you also represent that, like how the sine wave goes up and down over above the x-axis, like if it's a wave?
Oh, yeah, absolutely. Look, I mean, if you really want to look at it, sine 2t, right, is a sine curve but compressed into, so it's basically, I'm going to go like that. That's a full period in pi. So if you wanted to, you could graph that as your work.
That looks a lot more.
So now you can see, like, where did you have positive work? Between 0 and pi over 2? and then hold on.
Power before and then.
Yeah, pi over 4, right there. There it was. This was pi over 4. So we were getting positive work at pi over 4. We got 1. Anywhere before pi over 4, we had positive work. Once we get past pi over 4, we still have positive work, but it's coming down because we're starting to add negative work to this. And then it gets to 0, and then we come back. So, okay. Find, this time, it doesn't say find the work, right? But doesn't that represent work? Doesn't this right here represent work? So if this was a vector field, and this was a particle moving in that vector field, then this would be the work done. But that's not what they're telling you. They're just saying, hey, find the line integral over this vector field. So strictly by definition, this is equal to the vector field evaluated at the vector function r of t dotted with the derivative of r of t with respect to t. And you know what? I'll leave it as c here, even though it's not great notation. We need to figure out what our limits of integration are. But I will find that out once I investigate what r is. So r is this curve. It's the parabola y equals 1 plus x squared, which I think we're comfortable with what that looks like. X, y equals 1 plus x squared. But I need to write that as a vector function. And I'm only supposed to go between -1, 2, which is here, so I need to cut that off. And I'm supposed to go to 1, 2, which is here, cut that off. Right? And I'm supposed to go in this direction. So can you draw me that parabola with the vector function? Maybe I can help. Can you draw it with parametric equations? Okay, how would you do it? X is what? T, because x is free, right? Y depends on t, on x. So x here can be whatever you want. So we make that the t. And then the y is exactly this rewritten with x replaced with t. So 1 plus t squared. This is how I was telling you last class. You could use your calculator to graph every function you've ever graphed before. What are my restrictions on t? -1 to 1, because the restrictions on t are the same as the restrictions on x. And if I start it at t being -1, I'll be back here. And as I move through to t is 1, I will move along the curve and I will come this direction. Now, that's it as parametric. To write it in vector form, all we do is just throw those equations into here. So t, 1 plus t squared. We're going to need the derivative, aren't we? Now that we're kind of getting an idea of what we're going to have to do, I need the derivative, so let's go ahead and grab that while I'm here. This is 1 plus 2t. I think I have everything I need. We have the vector field, right? Here's the vector field, kind of ugly looking. All right, I think I'm ready. So this becomes integral from where to where? -1 to 1 of the field evaluated on the curve, which means I need to take my curve components, replace the x in my field with t, replace my y with 1 plus t squared into the field. Leave it as a vector though, right? So this will become x, which is t, over this. So it's this squared plus this squared, square root. So t squared plus 1 plus t squared square root. Well, I thought that was going to be kind of clean, but I guess not. And then the y, so I do 1 plus t squared over the same exact thing that I had over there, right? Any questions on that piece? This is the x, this is the y. Dot that with what? Dot that with 1, 2t dt? Yes?
Is that not supposed to be 1 plus t squared squared?
Yeah, I missed my square, didn't I? Yes. That's the y value is this, but then I've got to square it. Yes, it's on both of these. Thank you. All right, let's dot that out. I'm just having this really bad feeling that this is going to be horrible, but let's see what happens. Okay, this equals integral -1 to 1. All right, dot this 1 times the first piece. Okay, that's not so bad. T over the square root of t squared plus 1 plus t squared squared. But then plus, now this times this, which the 2t is like on top, so it just passes through and just becomes 2t plus 2t cubed over the same thing. All of this dt. How are you feeling about that integral? That doesn't seems a little ugly. Do we have anything going for us here?
Can't you combine them?
You can put them together. I agree. I agree with that. All right, let me see what that denominator is. What is t squared times 1 plus t squared squared? What is that? It's t squared plus 1 plus 2t squared plus t to the 4th. That's what that is. Which is just t to the 4th plus 3t squared plus 1. We good with that? I mean, that's what it is, right? That's what it is? Okay, so this becomes integral -1 to 1. What does my numerator become? Because I can put those together, right? 2t cubed plus 3t over the square root of t to the 4th plus 3t squared plus 1 dt. U sub. It just so happens that they made this problem work for you. What's the U sub? U is the whole thing inside the radical, right? So let's do it. We're going to go ahead and work this all the way through. The derivative of that is 4t squared plus 6t. That's what I meant to say, sorry. dt. There we go. That's what it is, right? Do we have 4t cubed plus 6t? No, almost, right? We have half of it. So we could see that if we factor 2 out on ours, we would have this. So this is where things are kind of weird. Like, I know that everyone learns substitution just a little bit different. So I never know when I do this, like how many students are like, what the hell are you doing? That is not the way I learned it. And I'm not here to try and reinvent the wheel. If you know how to do this, good. I mean, you're supposed to, but this is the way I do it. This is the way I usually teach my students to do it. It's a mix and match game. We try and tweak the right-hand side to make it turn into the left-hand side. I mean, to make it match up there. So I will replace this entire thing with 1/2 du. And everything on the bottom under the root is going to get replaced with u. So this integral becomes a new integral. This whole top became 1/2 du, so I'm going to put that back here, du, and then 1/2, right? 1/2 out here instead. And I'm left with 1 over root u. That's just, that's just u to the negative half, so antiderivative, that's just square root of u. Even if you have to take this into account also. But hopefully you agree with that. That's what that is. And now I'm going to switch back to the variable that I was working with, which was t. So I know that this becomes square root of t to the 4th plus 3t squared plus 1, evaluated -1 and 1, like that. Plug in 1. What do you get? Root 5? Minus, plug in -1. Root 5. Zero? So what is the conclusion? Given any vector field over any curve, the work is always 0. No. No. That, again, it's just to make this problem work out pretty nice. If you were to change the curve again and only do like half the parabola, go from 0 to 1 instead, your answer would have been in root 5. If you want to include more of the parabola, your answer is going to vary, right? I need to change those examples. I need to make them, I don't like the fact that they both turn out to be 0. I'm not happy about that. Any questions? Man, it's already 10 after. Now, just a little notation for you. There's an equivalent form of this line integral of the vector field. So this is the way that we say work, right? This is work, but if you see this, it is equivalent to this. So this is where we're saying, where are we going to see those come into play? Here it is. If your vector field has p, q, and r as its component functions, then if you take the line integral along C of the scalar function p with respect to x, so you're just looking at that one with respect to x, then add to that this one with respect to y, and then this one with respect to z, that is the same as doing this integral. So sometimes it might be a little easier for us to use the other version. All right, now this is a problem I took out of the book, and I know for those of you who've taken physics, you may have seen something like this, and there may possibly be an easier way to do it, but let's just stick with what we're doing in this class right now, okay? A 180-pound man is carrying a 20-pound tool bag, walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Note, work is measured in foot-pounds. Also, weight is a force. Okay, so your weight on a planet is a force. I hope you've learned that your mass is independent of, so, okay, all right. So everyone okay with the idea that weight is force? All right. So here's the picture. Here's the silo, like my silo. There it is. It's a 90-foot silo. It's got a 20-foot radius. And this man is going to walk around, go up with his bag all the way to the top. How much work did he do? So if I know this is going to be a work problem, right? Then what are the things I need? Work is going to be equal to line integral over c of f dot dr, right? So I'm going to need to know what is the field, right? What is the vector field? And I'm going to need to know r, which is the path function. So what would you like to talk about first? Which one are you most comfortable with at this point? You want to do R? Okay. You got to draw me this thing, right? Let's see. 1, 2, 3. Like, oh man, that's terrible. Seemed like at the end things went bad. Well, whatever. Okay. I have my computer drawing. It's even better. All right. So the guy goes around 3 times and he gets up to the top, right? Can you draw me that thing? I can give you some hint. If you look at it this way, it's just what? A circle. And what's the radius of that circle? 20, right? How would you draw a radius 20 circle with some sort of vector function? If I just asked you to draw me a circle, radius 20, you would do what? 20 cosine t, 20 sine t. But that would draw me just a circle on a flat sheet of paper. I actually want it to come up, right? Okay? So I'm hearing t. I'm almost there with you. Okay? Almost. Here's the kind of catch to it. I'm going to put right here question mark for a second. Right? Let's think about this. This component of the vector function tells me how high I'm going to be, right? So if I put t there, as I don't know if this is going to work, what is my restriction on t? Well, if you're going to use t here, it's got to be 90, right? But there's a problem with that. You need to draw 3 complete circles. So that's going to be the thing that's going to control your t. How do you draw 3 complete circles? Because that's what it says. He goes around 3 complete revolutions, right? What does your angle have to vary between? Because look, you're using trig functions, cosine and sine. What are you going to do to get 3 full revolutions? 0 to 6 pi, right? That's what has to be here, the way it's written. So this cannot be t, or else you're going to be 6 pi high. 6 times pi is about,
20.
yeah, it's not 90, is it? So that's not quite going to work. Understand? So, but you're on the right track. It's just it can't just be t. So what do y'all think? Think this through. At t equals 0, where do you need to be in terms of height off the ground? 0. And at t equals 6 pi, you need to be where? 90.
15 over pi t.
You're already reduced, right?
90 over 6.
There you go. Okay, we'll start with that. You want this 90 over 6 pi t. Look at this. That's what's going to go here. Now let's talk about y. At t equals 0, where are you? 0. So you're 0 height, right? At t is 6 pi, where are you? They cancel and you get 90. And this is linear, which means that as you go around, you're going up at the same rate, right? It's a linear incline. Does that make sense? Yes, go ahead.
Sorry, I just passed over my head. Where'd you get to 90 from?
Oh, the silo's 90 feet high.
Oh, that's right.
Yep. Make sense? You could almost do it this way. If you kind of uncoil that thing and straighten it out, if you uncoil it and keep its angle, that's the blue thing, but straightened out. This has to be 90, right? But the question is, how long is this?
It's 3 times the circumference.
Three times the circumference of one circle. What's the circumference of a circle? 2 pi times r is the circumference of a circle. R was, so 40 pi is the circumference, and then do what? Divide by? No. Multiply, divide? Is that going to work? No, that's not going to work. I'm trying to make a connection that would be easy. It's not going to work that way. Because you would need the actual arc length to get this side. Or I'm sorry, to get this distance. So let's not mess with that. That'll get uglier than it needs to be. I think just looking at this, most people can see the relationship. You need it to be linear because you're assuming the stairs are going up at the same rate the whole time, right? And you need it to be 90 at 6 pi and 0 at 0. So that'll work. All right, so far, is that all right?
Yeah.
Okay, now we'll need the derivative of this. Reduce the fraction, right? If you reduce, 6 goes into each of those. So 15 over pi t. Joel, is that the way you did it? How do you reason it the same sort of way?
Yeah,
Okay.
kind of that way.
All right, so we'll need the derivative in the integral, so I'm going to get it now. Derivative of this, negative 20 sine t. Derivative of that, 20 cosine t. Derivative of that is just 15 over pi. I need the field. What's the field? 0, 0, negative 180. Where are you getting that from? So the only thing we're assuming is acting on this guy is a gravitational force, right? But it's him in his bag. He had a 20-pound bag. 200, right? Yes? Negative. Okay, so negative 200 or positive 200? What do we want? Does it matter? It depends on what you're saying here. Do you want to know the work done by gravity, or do you want to know the work done by the man? You see what I'm saying? The force downward is gravity. He has to overcome that force going up, right? So he does work, right, which you could consider like positive work, or negative work would be the work done by the gravity. Make sense?
Yeah.
Why is it
So-
0, 0 again?
Okay, so why is it 0, 0? We are assuming here that when you look in three-dimensional space, like in this silo, right? This vector is pointed straight down, right? That vector is pointed straight down. We're assuming gravity is straight down. The negative 200 is his weight plus the weight of his bag. Understand? Now, we know that in reality, it may not be completely straight down depending on where you are on Earth, but for this problem, it's good enough, right? Okay. All right. Good? That's it. That's a pretty easy field, isn't it? That's a pretty easy field to work with. And I think most of you know from physics that you really only had to ever pay attention to his upward, that you didn't need to take into account any of this motion left and right. It's purely just the up and down opposing the force of gravity that matters. But we're going to see that in our formulation right here, aren't we? When we dot this with this, right? Because these first two components are 0, it's going to kill these two, right? Regardless of what they were. So it actually doesn't matter how he went up the silo. It's the fact that he got from the ground to 90, which is going to give you the force. Does that make sense? The left and right, front and back motion didn't matter. Just up. But do y'all see what I'm saying? I'm trying to get you to see that this shows you why it doesn't matter. Okay. All right, so I'm going to go back to this. This is, I know I'm going from 0 to 6 pi. I'm doing my force, right? My force with this curve plugged in, but my force doesn't have any variables, so I don't plug anything in. Dot that with 20, this one, negative 20 sine t. Did I say dot with that one? I think I did say dot with that one. I meant to point to this one, I'm sorry. The same thing though, it kills off these pieces. So all you're left with is this. 20 cosine t 15 over pi dt. And what do you get? Negative. Ooh, negative 3,000 over pi. Right? I'm integrating that from 0 to 6 pi dt. And this just becomes negative 3,000 over pi t evaluated from 0 to 6 pi. Why is what?
Why is it 6 pi, the upper bound?
Wasn't t from 0 to 6 pi?
We said,
See what?
we said 15 over pi, t.
No, 15. It was 90 over 6 pi t was the z component of the curve. Then the derivative of that was the z component of the derivative. But then the t restriction was from 0 to 6 pi. Yeah? Okay, now we plug in and we get what? 6 in there to cancel. Negative 18,000 minus 0. And what would that be measured in? Well, because we're measuring the silo in feet and the man in pounds, this would be, work would be foot-pounds. So foot-pounds. Foot-pounds. That's the work.
That is 15.
Sorry?
18,000.
I think it is. Yeah. All right. One more. I have enough time. I like this problem. There's going to be in the homework for this section, which I know all of you are going to do. They're going to have, there's quite a few word problems in this, or not word problems, but just more like this stuff towards the end. So just be prepared for that. A 10 kilogram object moves with a position function R of t is sine 4t sine 8t t squared with t between 0 and 1. Find the work done on the object during this time period. Any ideas? Well, they want to know what work is, right? Okay, so we're going to need R, but we have it, and we're going to need R prime, right, to get our formula. So work is going to be integral, line integral, F dot dr like that. R is given to us by, like we didn't have to work for it, did we? It's there, it's provided. It's nice. I wish everything were free. I wish everything was just given, right? All right, so you want the derivative? What's wrong?
You're like, I wish everything was free. I'm like, speaking of which,
Oh.
stop grades.
4 cosine 4t is the derivative of this, right? And then 8 cosine 8t is the derivative of that, and then this was 2t. So I'll need that in my formulation for this, right? Anyone notice something's missing here?
The field.
The field, right? But like last time, what we did is, well, the man was 100 and something pounds, and we just said that the field was this thing. What's the difference between that and this? We have 10 kilogram object. That's his mass. So, or that's not his, it's an object. I don't know if it's a he or a she or if it's anything. It's 10 kilograms, right? It has mass. Mass is not a force, right? Mass is not a force. So right now, the field is still a question mark, isn't it? The field is still a question mark. I need a field, though, and for a field, I'd like to, since I'm talking about work, I'd like to see what the force vector is, right? So how can I get force if all I have is mass? So this is, again, some physics. Force equals mass times acceleration, right? Acceleration. Yes? You agree with that? But, if I have, when I say acceleration, it's the acceleration of the object. Not the acceleration of gravity, it's the acceleration of the object.
So we take the second derivative.
There you go. So look, if this is your position function, the first derivative is your velocity function, the second derivative is your acceleration function. So if I want to know what the acceleration of this object is, I take its second derivative. Which is because this was velocity, right? So I take the second derivative and I get negative 16 sine 4t. And then I do derivative of this and I get negative 64 sine 8t. And then derivative of this I get 2. That's your acceleration function. Then if I want the force as a field, it's the mass times the acceleration function, which is going to be, well, mass is 10, right? Multiply this by 10, it's a scalar. So you get negative 160 sine 4t, negative 640 sine 8t, and then 20, yeah? There's your force. Pardon me?
Could you just pull the mass from it?
Yes, you could have taken the mass out of the whole thing. But if it was not given, like if they said the mass of an object is m, you would want to pull that out. If it's 10, then you may as well keep it in. But you can take it out. It doesn't matter. All right, so all I need to do is dot these. What, dot these? I said these. What do I mean? I need to dot my force with r prime. But what? Good question. Don't you need to plug in the r into this? Well, this is already in terms of t. So we don't need to do that. It actually came from that, right? But so we're good. We just dot those two together.
Yeah, that's why I said go ahead.
Do we have a restriction on t? It was given, right? 0 to 1. Dot, dot, dot. Here we go. So this times this. So negative 160 sine squared 4t. Right? Oh, I'm sorry. Who? I don't know why I pointed up there. This times this. Negative 640. Is that right? 640. Sine 4t. Cosine 4t. Y'all good with that? Here and here. Then I got to go here and here. Maybe we should have pulled that 10 out. What is this going to be?
Negative 5,120.
Negative 5,120. Sine 8t. Cosine 8t. And then finally, 20. That one I don't mind doing. 40t. And then dt. How are you going to handle this right here? Sine 4t, cosine 4t. Double angle formula, turn that into what? Sine of 8t, but half of that? So scale to 640. I hope everyone's comfortable with that. These are those little things that I do that I just don't know. I remember as a student like not knowing how the teacher did something, and here I am doing the same thing. This is negative 320, what, sine 8t. Okay, I'm going to have to stop. Negative 320 times 2 sine 4t cosine 4t. That's this right here, right? Nope, not distributed. Then this, using the formula, is sine 8t. So go back and look at your double angle formula. Sine 2u equals 2 sine u cosine u. So that's your double angle formula, but replace that with 8t. And then this one, same thing, right? I can do the same on that. So minus, what's half of that? 2560 sine 16t. And lastly, 40t. I don't have to change that. And then I get to integrate. Am I out of time? No? Okay. So we get to integrate. Go ahead and integrate that. I'm wondering if I took this problem out of the book. I thought maybe I had taken this problem out of the book, but I don't see it in here. All right, well, it is what it is. Y'all, what did you get? You got a final answer?
Yeah, well, I mean.
What did you get?
For the integration or for the?
Like everything?
Oh.
No? I thought you were saying you got everything. Y'all think y'all could do that from there?
Oh, yeah.
Okay. All right. You get the idea, hopefully. All right. So just so you know, last night I was going to grade your test, honestly, the ones you had turned in. I sat down, and that's when that hailstorm came in and just ruined my night. And so I don't have those for you. The ones you just turned in today, I've got to grade those also. But I'm giving 2 exams tomorrow for my Cal 2 and for my college algebra. I promised them I'd have their tests graded by Friday so that they could drop if they needed to. So that basically what I'm telling you is that I'm not going to get to yours until this weekend. My intention is to have both your mini exams back to you Monday, and then I'll give you your new one. I believe the new one will be the last one. All right? We're good? We start 13:3 next time. We're doing good time-wise, I think.
So we made up for that one day?
I don't know if we made up. All I know is we have 1, 2, 3, 4, 5, 6, 7 more sections, and I think we have more days than sections still.
We have 4 more, right? 4 more days?
Till the end of the semester?
Without the finals?
Is it 4? No, it can't be 4.
Or it's just 2?
I hope it's 6.
I thought.
We don't have 2 more weeks left. Is that right?
I thought this was. I thought we have 2 more weeks left.
Hold on a second, man. When's our last day?
Because May 13th, I think.
It's early, man.
No, it's not. That's late. We have the 18th, the 20th, the 25th, the 27th, the 2nd, and the 4th. And that's it. So we have 6 more meetings.
We have 6 more meetings?
6 more class meetings. And then the final is the week after that. No. Well, we're not. I'm saying I have 7 sections to cover in 6 days.
Oh, okay.
It's going to be tight. It's going to be real tight. Live streaming, yeah.
Oh, hey, you know.
I usually just barely am able to touch the last section. But the last section's really clean. It's just like, here's a formula. Boom. Like we get to a final result and it's good.
You know that girl in our institute, the tall one? Yeah. She's gonna do this.